I want to know how the structure changes as I move away from here. How the structure changes. So basically, I want to know the structure in this immediate region. This is the structure. So what is the nuclear structure? In the immediate periphery. Because I cannot move very far away. The nuclei will be very less, they will have very less lifetime, more and more unstable. Okay, so some nuclei which is very close here, it will be say unstable, lifetime is 1 millisecond, but if I go far away, suppose here, then the lifetime is probably 10 to the power minus 28 seconds. I am just unable to detect this, okay. So this is the way. So I am trying to find how the nuclear structure changes in the immediate periphery. Okay, so this is what I want to do. Good. Now I am rubbing this. Okay. Now let me talk about the model. The single most important model in nuclear physics. And you know what that model is? That's shell model. Unfortunately, in your textbooks, you will see that it's written that shell model can explain only single particle behavior, not collective behavior. What about collective model? It explains collective behavior, but not single particle behavior. But they were very old. Wherever you will find these things. The correct interpretation or the correct explanation is that there is nothing that shell model cannot explain, both single particle and collective. What we lack is interaction and the technology to do the calculations. Okay, keep this in mind. So that's why I will say that shell model is the model of nuclear physics. Okay, now what happens in shell model is basically, let me briefly tell you what is happening. First, when I am trying to understand the structure of some quantum system, forget nuclear physics. So right now I am talking about quantum mechanics. I am using a potential to understand the structure of a quantum system. Why? What is nucleus? Nucleus has protons and neutrons. Now, of course, they are bound together. So basically, they are quantum system where we have two types of particles. Since they are bound together, so there is a potential well. Good. Now, every potential well will have what? Its own eigenvalues and eigenfunctions. That means energy level, right? There will be ground state energy levels, excited state energy levels. Each excited state, they will have lifetime, which will tell you about the transition probability and all that. So these are the basics. Now, so I am doing a model, shell model. So what will I choose as a potential? The very simplest model that I can easily work out, and that is a harmonic oscillator potential. Okay. I know its solutions, and if you move away a little bit from away from stability, the behavior is harmonic in nature. Okay. The first term, the x term, it vanishes due to maxima minima condition. So the second term, which is important, is x square, which is harmonic in nature. This is the first reason of choosing harmonic oscillator potential. Second reason is its solutions are easily known. Okay. So now, if I do a harmonic oscillator, you will find that the nature of the energy levels, so they are equidistant. And if you put your protons and neutrons of any nucleus in them, you will not be able to correctly understand or correctly, what should I say, explain the magic numbers of nuclei. That means some nuclei are found to be stable, as if there exists a sort of cell structure in the nuclei. And to explain that, we have to add a sort of bunching. That means what I need is something like this. I need a sort of like this. The levels not together, but I want the levels to be bunched together. Okay, a bunching of levels. I need like that. Now, do you know the structure of our Milky Way galaxy? Let me move entirely outside. It's like a spiral, okay. The Milky Way galaxy is like a spiral, okay. Now spiral doesn't mean that it will have infinite arms. There also we have got only certain arms, as if there is a sort of bunching together of all the arms together into bigger groups. Even in the Milky Way galaxy, this is a macroscopic observation. This is a microscopic quantum mechanical observation. See the similarity. So this is how we can explain, by this bunching of levels, we can explain the magic numbers. Okay. So then what we did, we added some alpha into L dot S interaction to the harmonic oscillator potential, and we observed this bunching of levels. Now the reason for this L dot S is entirely what? Relativistic in origin. Okay, this L dot S nature, and also it's a surface effect. I will explain this some other time. Anyway, so this is the overall picture of the shell model. Now, you see, so overall after all these calculations, there is actually yet another harmonic oscillator plus L dot S plus yet another L squared term. It is also added, keep this in mind, so as to reproduce the levels. Okay, this is also added, L squared interaction. Now, after all this thing, we have got what is known as, remember we have protons and neutrons, so pi I am using for proton, nu for neutrons. So I will have energy levels for proton and neutron, and the nomenclature is like this: 1s half, 1p 3 half, then 1p half, next 1d 5 half, then 2s half, then 1d 3 half. Okay. Now let me show it to you. Basically this is single, these two are bunched. Okay, this is single. Again these are bunched together. Fine. Now this is what we observe in normal nuclei. What is normal nuclei? That is nuclei which we find in the valley of stability. Okay. So this is more or less the behavior of nuclei in the valley of stability. But as we move away, what happens? What do you think will happen? First of all, do you think the levels will remain like this, or there will be an overall shifting of levels? Now, this is the overall feature for stable nuclei. Now, suppose let me talk about neutron-deficient nuclei. Neutron-deficient nuclei. What are they? So basically, from stable nuclei, whatever neutrons and proton combinations are there, if some of the neutrons are less compared to the stable nuclei, we get neutron-deficient nuclei. So there the effect of protons will be larger, you can say. Because you see in this plot, where will you find neutron-deficient nuclei? Tell me. In this plot. So if I move away, here you will find the neutron-deficient nuclei in this region. Okay. Now, so here effectively the effect of protons will be larger because the neutrons are less to counteract the effect of Coulomb interaction, if you think away from the strong interaction. So what actually happens is that in this neutron-deficient nuclei, these levels and these levels which have been more or less together, what now happens is that all these proton levels, they shift upward compared to the neutron levels. Neutron levels remain the same. So as if you can say, now the situation is like this. See, there is an upward shifting overall for the proton levels. So this is the proton, These are the proton levels and these are the neutron levels. So there is an upward shifting of all the proton levels together. Previously they were all together, right? Now the result will be that of this shifting. Very soon some of the levels, say what is above 1D3 half, there will be say some D5 half level. This will become unbound. So all the levels above will start becoming unbound. Previously they were all bound together, but now some of them will become unbound, whereas other of the proton orbitals are bound. So now you understand. Previously the nuclear structure study using shell model, we assume that all the levels are bound. But now when we are doing the analysis, we will find that some of the levels have become unbound, whereas some of the levels are bound. So the calculations will become extremely complicated. Okay, so this is one of the major differences which we observe when we move away from the valley of stability, right now towards the neutron-deficient side. So you see what is happening, why is the overall shift? The effect of protons is more over here, right? The effect of protons is more. Now protons is more means they will be repelling each other. So the effect of Coulomb interaction is more. Okay. Now the effect of Coulomb interaction is more. So overall the interaction energy will be less. Interaction energy will be less. So this means in the potential the energy levels will go higher. Right? If there is more interaction, the levels will be lower. If the interaction decreases, the energy levels will go higher. So this is the effect. So effectively what we have learned is that if this is your harmonic oscillator potential, now the proton and previously the neutron. Now what is happening is that the proton levels are now much higher compared to your neutron levels. Right now this is what is happening, and these proton levels are now even above. So yes, so in a way now we have got this many unbound states. So previously all the calculations that we have to do, they were between the bound and the bound states. Okay, and the reaction channels which were there, they were separate. So previously reaction and bound spectrum, the calculations were different. But now what is happening is that when I am doing the calculation, then I have to consider, what do I have to consider? I have to consider the spectrum from this particle, everything. Okay, so I have to consider, when I am talking about nuclear structure, I have to consider the excitation from this particle in this unbound state. Again, one proton from this state, one neutron from this state. Now the neutron is in bound state while the proton is in unbound state. So now for this drip-line nuclei, what is happening is when I am trying to do a structure calculation, I have to mix both the bound and the continuum states. And as a result, what is happening is previously the nuclear bound structure and the reactions, the calculations were different, but now they get intermingled. Okay, so this is what we mean when we talk about the change in the structure as well as reaction as we approach the drip-line nuclei. So this is a fundamental change. This is not an easy change. The calculations will become very much involved because now we have to consider both the unbound and the bound states. Okay, so these are bound and these are the unbound states. So this is one of the most important changes. Now another even more fundamental change that you can expect is the following. So see, if this is my NZ plot and this is the value of stability, and right now suppose I am talking about nuclei in this region. Okay. Suppose, so these are the proton-rich nuclei, these are the neutron-rich nuclei. So I am talking about this. Now try to understand, when I am talking about this nuclei in the value of stability, the number of proton and neutron here in the nucleus is entirely different compared to the nuclei over here. Right? Now, in any quantum system, you do know, in any quantum system, if the constituents, they change, their interactions, they change, then what will change as a result? So in a quantum system, if the constituents, the numbers, say for example, they change, and as a result, not only the numbers, the interactions also change. So as a result, what will change is that the single particle levels and the wave function, that is energy eigenvalue and energy eigenfunctions, they will change. So the change will happen differently. Here, the changes will be different, because here the number of protons is more or number of neutrons. Which one? See, this, yes, this is neutron-rich side, right? Or wrong? Tell me, is there something wrong? Yes, this is neutron-rich. See, the number is much more compared to over here. So this is the proton-rich side, p-rich side, and this is the n-rich side. So now, effectively, what is happening compared to your normal region, here there are more neutrons, here there are less neutrons, in a way. Sometimes even more protons than neutrons. Now, because of this, the potential entirely changes. So, in these three regions, effectively, I have got different potentials. And as a result of this different potential, what happens is that I have got different energy, eigenvalues and eigenfunctions. So effectively I mean different single particle energy levels and their lifetime. Okay, so overall, in terms of shell model, what does this mean? This change means that since we have got a different potential, so the energy levels will be different. Now, the energy levels, if they are different, then the bunching will also be different. So, the bunching will also be different. Bunching is different. And all of these differences is because of this different potential, which is effectively due to different number of constituents and different interactions between those constituents. Okay, this is important. So the change goes like this, and the result is different single particle energy levels and lifetime, as well as different bunching. And the moment we have got different bunching, the result is very eminent, which is we have now got different magic numbers. Because magic numbers, their existence is all contributed to the bunching. So if the bunching changes, the energy levels, even the ordering, see, different energy levels, this means the bunching is different and also the energy level ordering is also different. Now this difference is not always there, but slowly and gradually the difference moves on. Say for example, you have got 1s half, right? Then 1p3 half, then 1p half, then yes?
Yes.
No, 1d5 half. 1d5 half, then 2s half. Okay, and next we have got 1d3 half. Now it can happen in certain nuclei that this can change. Say for example, 2s half comes down and 1d3 half goes up. This change is possible, but this doesn't happen for this nuclei. This can happen for nuclei which are either neutron-rich side or on the proton-rich side. Why? Because for them the potential will be different, and the difference in potential causes the change in energy levels. So see, the gap changes as well as the ordering also changes, and the overall effect is change in the magic number, and this has been experimentally observed. As we slowly move towards the neutron drift line or proton drift line in any region of the nucleus, whether it is light nuclei, medium or heavy, slowly and gradually there are indications of changing magic numbers. So there is nothing separate about magic number. They are simply effects of the potential, nothing else. They are not the cause, they are the effects. If the potential changes, the energy levels will change, the ordering of the energy levels will change, the bunching of the energy levels will change, and the magic numbers can change.